बच्चेच मेंबर आहे. नाही मुलगा आहे शांतनु.
उद्या चालू
सुरू
एक मिनिट यार, यांनी
आपण केलेलं आहे ना.
चालू कंटिन्यू.
ठीक. Application of derivative. Application of derivative consists of subtopics. First, rate of measures, maximum and minimum, slopes of tangents and normal and their equations. Next, approximations. Fifth, increasing and decreasing function. Increasing and decreasing functions. These are the 5 subtopics in applications of derivative. Now, rate of measures. This is the application of maths as well as physics. Physics includes your surface area, volume, etc. Maximum and minimum functions and increasing and decreasing functions, somewhat identical but slightly different. Slopes of tangents and normals and their applications and equations. This includes somewhat your conics also. And approximations, you have to calculate the approximate value of particular functions. So these are the 5 subtopics including your application of derivative for your competitive exams like JEE and CET. One by one we discuss each and every application shortly and then take some examples. Now concentrate. First, we going to study the topic first, that is in rate of measure. In this topic, area, volume, at the same time we require S means displacement, V means acceleration, and most important, A is acceleration and V is velocity. Now, area, volume. For circle, they are functions of radius, and for another figures, they are functions of sides. for conics means cubes, they are functions of sides. Now, most important thing, for cylinders, they are functions of radius as well as height. And for cones, they are functions of radius, perpendicular height h, and also slant height h. So, during calculations for cylinders and cones, one parameter, radius or height, is constant. Here for cones, radius is constant or height is constant or slant height is constant. Then we calculate rate of area or rate of volume. Displacement, general, this equation is given to you in the form of time. Velocity, velocity is rate of change of displacement with respect to time. Means you have to differentiate equation of displacement with respect to time. And acceleration now, acceleration is rate of change of velocity with respect to time. Rate of change of velocity with respect to time, or it is the derivative of with respect to time ds upon dt should be equal to d2s upon dt square, that is second order derivative of displacement. These are the some basic information regarding rate of measures. Let's take one suitable example. For circle, if r is radius of circle, then our aim is to obtain relation between rate of increase of area of circle with respect to volume. With respect to volume. But circle has no volume. For that purpose, we take instead of circle, sphere. Now, area of sphere 4 pi r square. Volume of sphere 4 upon 3 pi r cube. So rate of change of area with respect to volume. Rate of change of area with respect to volume should be equal to rate of area. It is related with radius and volume is also related with radius. So 4 pi, derivative of r square 2r, 2 4s are 8. 8r upon 4 upon 3 pi, constant term. Derivative of r cube 3r square. Pi gets cancelled. 3 gets cancelled. 1 radius is cancelled. Should be equal to 4 1s are 4. 4 2s are 8. That is 2 upon r. But 2 is constant. So rate of change of area with respect to volume is inversely proportional to radius. In this way, we can calculate rate of measures. Now, another part of application of derivative is means rate of measure is when displacement equation is given and our aim is to calculate velocity and acceleration. So in this case, equation of displacement is given. Now concentrate. S equal to, say, 4t square minus 3t plus 7. This is the equation of displacement. Now, our aim is to calculate velocity and acceleration when time is 2 seconds. Now concentrate. Velocity is rate of change of displacement with respect to time. Should be equal to, concentrate, derivative of 4t square, 2 4s are 8, 8t minus 3. So at t equal to 2 seconds, velocity equal to, substitute t equal to 2, 8 2s are 16, 16 minus 3, 13 meter per second. And acceleration is change in velocity with respect to time. So velocity is 8t minus 3. So derivative of this, t is 1 into 8, derivative of 3 is 0. So your answer is directly 8 meter per second square. Okay. Now next part of same rate of measures. In this case, errors are given and our aim is to obtain errors in the measurement of some particular functions. For example, error in measurement of radius is say 2%, and our aim is to obtain error in the measurement of surface area of sphere. Surface area of sphere. Now, error in the measurement of radius is 2%, and our aim is to obtain surface area of sphere, means error in the surface area of sphere. So, surface area of sphere A is 4 pi r square. Now, this function 4 pi is totally constant. Concentrate on r square. We know if error is a%, then error in the measurement of n raised to n, that is n times a, n into a%. Here a is r square, power of r is 2. So error in the measurement of surface area, quite simple, power is 2 into percentage error in the r, that is 2%. So 2 2s are 4. Error in the measurement of area of sphere, that is surface area of sphere, is 4%. This is one simple trick in the solving problem for your competitive exams. If error in particular function is given, say error is a%, in measurement of m term, say, then error in measurement of m raised to n is n times error in m. What is error in m? A%. This is your direct answer. No need to calculate. This is one shortcut for solving MCQs. Take another question. Suppose error in measurement of length is 2%. Error in measurement of breadth is 1.5%. Then for this rectangle, error in measurement of area is how much? If it is a rectangle for length and breadth given, error in length is 2%, error in breadth is 1.5%, then error in measurement of area will be how much? Options are given: 1.5%, B 3%, C 4%, D 2.8%. So, in this case, area is length into breadth. Area is length into breadth. When multiplication will be there will be a addition of area takes place. Means 2 plus 1.5. 2 plus 1.5 is 3.5%. Always, whenever multiplication of terms are there, area is given in the form of summation. Now, 3.5 answer is not there. So, your answer approximately is equal to nearest value 3%. In this case, you take approximate slightly lower value, not higher value. 4 is higher, 3 is lower. This is also one trick to solve the MCQs. If instead of area is given, some functions are there, say A is same equation, same part, 2%, B is 1.5, and our aim is to obtain error in the measurement of L square into B, or L raised to M into B raised to L. Then how to calculate error in this measurement? Should be equal to M multiplied by error in measurement of length plus N multiplied by error in the measurement of breadth. Means M into 2%, that is 2M, plus N into 1.5, all is in percentage. If M is 1, N is 2, then error is 2 into 1, 2, plus 2 into 1.5, 1.5 into 2, 3. So error in measurement is 5%. In this way, we have to calculate the error in the measurement of particular part. Next, suppose some problems are there. A stone is dropped in a point and circle is formed. The rate of increasing of circles, means waves, is proportional to R. Is proportional to R. R is radius. The rate of R with respect to time is given as 3 centimeter per second. Radius is given as 1 centimeter. Our aim is to obtain rate of increase of surface area or rate of increase of area of these circles. Means our aim is to calculate dA upon dt. Now for circle, area is pi r square. Therefore, rate of increase of area dA upon dt. But here A is function of radius, So it should be equal to pi constant term derivative of r with respect to time, that is 2r dr upon dt. So 2 pi constant, r is given as 1, dr upon dt is given as 3. So 3 to the 6 pi centimeter per second square or centimeter square per second. Centimeter square per second. This is rate of change of area with respect to time for a paddles in which stone is dropped on the pond. Similarly, we can calculate in this case rate of change of area with respect to circumference or rate of change of circumference with respect to area. Now concentrate. In circumference as well as area, they are functions of radius. So A is pi r square, circumference C is 2 pi r. So if you calculate rate of change of circumference, then that is 2 pi dr upon dt. And rate of change of area dA upon dt should be equal to r square derivative 2r dr upon dt. So pi into twice r dr upon dt. So rate of change of circumference with respect to surface area, that is rate of change of circumference with respect to surface area, should be equal to 2 gets cancelled, pi gets cancelled, dr upon dt gets cancelled, answer is just 1 upon r. Means rate of change of circumference with respect to area directly inversely proportional to r, and rate of change of area with respect to circumference is directly proportional to r. These are some tricks for solving problems on circumference area are given. These are some basic tricks. So this is the first part of application of derivative, that is rate of measures. Now some problems regarding your mensuration part was also there, particularly cones and cylinders. You must know the formula for surface area, curved surface area, total surface area of cylinder, cone and cubes and cuboid. For cube and cuboid, the radius is not there, the sides are there, and for cylinders, cones, there will be a radius as well as perpendicular height, as well as for cones slant height also there. Let's take some examples. Now for cube, the surface area means total surface area of cube is 6L square, where A is side, and this is total surface area. For cube, volume is L cube. This is volume. So rate of change of volume with respect to surface area. You have to differentiate these equations now, this formula with respect to length. So derivative of L cube 3L square. For this 6 to the 12 12L. So rate of change of volume with respect to area of cube is L gets cancelled, that is L upon 4. Means in terms of proportional, rate of change of volume of cube with respect to area is directly proportional to the length. And if equation is the reverse, then it is inversely proportional to the length. This is some trick to solving problems regarding cube. Now, after cube, cylinder will be there, and cylinder consists of slant height, rather perpendicular height and radius. Cone consists of slant height, perpendicular height and radius. So one by one we take these examples. Now for cylinder. Now here two parameters are there and one parameter is said to be constant, either radius or height. So initially, if height is constant, if h is constant, then for cylinder, the total surface area is two pi r plus h. This is total surface area, say 80. Curved surface area, two pi RH, and volume is pi r square h. So first we take these examples, curved surface and volume. So rate of change of curved surface with respect to volume of cylinder dA upon dV. Now 2 pi h is constant, so only derivative of r will be there, and derivative of r should be 1. So your answer is directly 2 pi h. Now for volume, pi and h are constant. Derivative of r square 2r. So 2 h pi gets cancelled. R means for cylinder, rate of change of curved surface with respect to volume is inversely proportional to R. Is inversely proportional to R. Next case will be cone, but cone has different characters. Cone consists of perpendicular height, radius and slant height. But generally, problem regarding radius and height will be there. Concentrate. For cone. Now, surface area. That is curved surface area is pi r h and volume 1 upon 3 pi r square h. So, rate of change of surface area with respect to volume of cone will be, if r is function of time, then pi h dr upon dt divided by 1 upon 3 pi h, if r is function of time, 2 times r dr upon dt gets cancelled. Pi also gets cancelled. H also gets cancelled. So your answer is 3 upon twice r. Substitute value of r if it is given, you get the answer of dA upon dt. You can separately calculate rate of surface area with respect to time, that is dA upon dt, and rate of volume with respect to time, dA upon dt. In this case, radius is function of time because height is constant. And if radius is constant, then height is function of time. In this way, you calculate these parameters. This is the first part of application of derivative, rate of measures. Now, the second part is slopes of tangents and normals and equations of tangents and normals. So, slopes and equations of tangents and normals. Now concentrate. Tangents and normal, they are exactly perpendicular to each other, and when particular lines are perpendicular, their slopes are negative reciprocals of each other. So in this case, if you calculate slope of tangent, then slope of normal is negative reciprocal of that of tangent. But how to calculate slope of tangent? Suppose for any curve, the equation of curve is given as, say, y equal to 3x square minus 2x plus 5. This is just simple equation. But curves are circles also, parabolas also, hyperbolas also, or ellipse also. So this is just simple example of curve which is a function of x. So at point x1 and y1, at point x1 and y1, the equation of this curve 3x square minus 2x plus 5 at point x1 and y1, the slope of tangent is should be equal to dy upon dx. Here y is function of x, that's why I will write dy upon dx at point x1 comma y1. So derivative of 3x square, 6x, derivative of x is 1, that is 2, derivative of y is 0. So at point x1 y1, the slope is, say, m equal to 6x1 minus 2. You know slope for tangent. So equation of tangent by slope point form. By slope point form. What is slope point form? Y minus y1 equal to m x minus x. Y minus y1 equal to m x minus x1. Substitute the value of x1, y1 and m. You get equation of slope, equation of tangent, and this is slope of tangent. For normal, its slope is negative reciprocal. Same points are there. Substitute the value of minus 1 upon m here, and you get equation of normal also. This is the part of slopes and equations of tangents and normal. After break, we take some examples also. Thank you.